on that day, plus free chance notes.
Yeah, cheaper than them guys that buy me.
Probably good. You know, I don't want it to be like recording too loud.
All my diagram.
Still have about 40 seconds to go. I can walk my kid to school, elementary school, and I can count down, you know, to the bell, and it's accurate to the second, to the fraction of a second. So all the kids were so impressed. It's like, okay, the bell is going to ring in 5, 4, 3, 2, 1, and they go like, woo! And then the bell rings, of course.
Awesome.
You don't need to write that
I get distracted.
I just want to show you something. I have started a Twitter channel or Twitter account, you know, for ARC-CIS. So I'm basically representing the department and just kind of post stuff that I think is kind of interesting. So it's just ARC-CIS. If you have a Twitter account already, you can just go there and follow, you know, the articles. Some of those are, I try not to put in anything that is, you know, too tech, you know. Okay, you know, stuff that, you know, people would actually care about. Let me see. Okay, so the latest one is got an ink guzzler printer and try, you know, this. So I'm getting this to try on my own printer. Do you guys know what it is? Does anyone have, you know, this already installed on your printer? Yeah? No? Okay, so you guys know about, you know, inkjets. You know, you can buy, you know, refill kits, you know, that comes with a syringe and you can refill the kit. But it's still troublesome. I mean, that's still, you know, you have to take the ink cartridges out. You know, it's kind of messy, and you have to do it fairly frequently too, depending on the capacity of the reservoir. So what this does is they have a big, you know, reservoir on the outside of the printer, and it feeds, you know, the actual print head or the little cartridges in the inside. So it's continuous. So, you know, how frequently you have to refill that tank depends on the size of the tank. If you have a large size, you know, it's good for, you know, it's equivalent to 6 or 7 of the little ink cartridges in the inside. So I'm giving it a try because, you know, the cost of something like this is about the cost of 4 ink cartridges. So there's not much to lose. Okay, there really isn't much. There isn't much to lose. So I'm gonna give it a try and find out, you know, whether it works well or not. So basically, if you want to, you know, hear news like that, also if you want to try the true type fonts, I mean, some of you, you know, probably want to do things about, you know, fonts and whatnot. This is a really cool website. I just found it recently, but it has got, you know, sci-fi fonts. And the sci-fi fonts include Transformer, Space Jedi, Batman Forever, Tron, and so on and so forth. So next time you type your English paper, you can pick a font that fits the content of your English paper. If you get an F because of that, don't blame me. There's another website that's even cooler. I think it's a website for sci-fi, you know, fans, and that one has got, you know, fonts for Vorlon and Shadow languages. That's really cool. So, you know, random stuff. Sometimes it's random stuff like that, and sometimes it's, you know, fairly useful tools like I guess it's called hugging or hooging. I don't know whether it's, you know, short U sound or long U sound because you know, by spelling rules, you know, it should be a long U sound, right? It should be hooging. I don't know. Yeah, I probably should read the about page and see how it's pronounced. But this is a really cool tool. I used it, and what it does is, sometimes, since, digital cameras are so cheap now, so sometimes when you go to a place, such as, any type of monument, any type of park that is really, wide, and you want to capture a wide angle, capture of the place, and you don't have the money to buy, a really wide angle lens or a camera that has a wide angle lens, what this does is it allows you to take like lots and lots of pictures, and then allows you to stitch it all together. Yep.
My sister's phone, it's installed.
Sorry?
My sister's phone, it's a simple phone, and it has the programmer in it. You take lots of pictures, and it combines the pictures together.
Okay.
They have that for
Yeah, they have that for regular cameras too.
Wait. Hold on. I bet you your camera cannot do this. Okay, you can do multi-roll. You can also simulate architectural projection. So basically, you can start with a picture that looks like this with all the converging lines, and you can adjust it so that it is not converging anymore.
Oh, that's straight. That's so cool.
That's cool.
Now to do something like this, traditionally to do something like this using camera lenses, you need at least a tilt shift lens. Those things are easily $1,200 each, not counting the cost of the camera itself. But to do this, you just need your good cheap old camera. And the best thing is when you're doing this, you can also combine it with the stitching of multiple images into one. So now, if you have one of those El cheapo digital cameras that doesn't have a good zoom, it doesn't matter. You just have to take lots and lots of pictures of the same thing. You do have to spend some time to tell the software all the vertical lines and all the horizontal lines. But once the software understands, okay, this is a vertical line and this is a horizontal line, it will be able to stitch everything together. So I think it is really cool. You can stitch pictures from different lenses and combine those. Mosaic mode, perspective correction. This one is quite impressive. You can see how a picture like this got corrected to be a picture like this. Okay. And it shows you, the tutorial actually shows you step by step, how to do it. It's not just push this button and everything is done. It does involve quite a bit of work on your part. And also you have to be aware of this when you take a picture to make sure that in the picture you have some references of vertical lines and horizontal lines. But I think since it's free, you got nothing to lose except your time. Okay? So next time you go on a trip and you want to capture some really nice scene like a beach or at the top of a hill or something like that, this is this is a pretty good software to get. I know your phones can do some of this stuff here, but this can do a little more than that. It actually gets the camera lens properties from your EXIF tag in your picture, and it will do all the corrections based on that too. Pretty neat stuff for free. I mean,
What's the salt weapon? Sorry, what's the salt weapon?
What is what?
The automated assault
salt
weapon.
Oh, this one?
What is that?
Iron Man.
A future for drones, automated killing. So it's a flying drone, and if you read this article, it was being tested, and it was only programmed to look for the tarp, a tarp with a certain color combination. So the two drones would fly around to look for that pattern, and once they locate a pattern, I think they either fire some fake weapon or actual weapon because it's only a test, onto the tarped area. And if you combine this with facial recognition, there's some pretty interesting combination there. Okay, facial recognition is not killing for killing anymore. You guys already know that because with Picasa, the Google Picasa photo album has the ability to do facial recognition. In other words, you can give it like 2 or 3 pictures of grandma. Okay, so this picture is of grandma. This is also a picture of grandma. This is also a picture of grandma. So the system would learn what grandma looks like. So in the future, you upload all your family reunion pictures and whatnot, to Picasa, And then what you can do now is to say, I want to find all the pictures with grandma in it. And then they will go through all the pictures that you upload and do facial recognition to find grandma. And they will give you a list of those pictures with grandma in it.
And then send a drone to go get her. No.
And now we just have to, now we just have to hook up Picasa to the drone, and we are all set.
Go get grandma.
Or someone, right?
I think the drone will run out of fuel.
Huh?
The drone will run out of fuel.
The drone will run out of fuel. The drone cannot fly slow enough to catch up with grandma. It's like, phew! Oh, okay, we have to make another pass. Turn around. Phew! Oh, we have to make another pass. Yeah, they have to turn these drones into powered parachutes. You know, those power parachutes, you know, they fly really slow and they can stay up, you know, for a long time, and they're cheap. They're dirt cheap. Okay, so once they turn the automatic drones into those things, you know, losing one or two is not a big deal. You know, it's a few $100 each, right? But the defense contractors probably won't like that idea because they won't make money out of it. One screw for one of those high-tech airplanes is more than this drone. So anyway, so I post articles like these, 3D headgear, 380 virtual 75-inch display. So that's kind of cool too. So kind of things like that, some are useful, some are not so useful, maybe even statistics of jobs, Outlook and stuff like that. So things that I think would be kind of interesting to people like yourself. All right, so back to the boring stuff. Are there any questions about the exam on Thursday? Yes, there is one on Thursday. Any questions about the material? Yep.
Could we just do one of those substitutions?
Yeah, pre and post.
Okay, pre and post. Okay, we can do
Yeah,
that.
just to do it right or whatever.
As a practice.
Yeah.
And also, is there going to be a reverse one on the?
Yes.
Can we do
Those.
Can we do one of those too?
Yeah.
Well, let's combine and do a reverse one because the reverse one will ask you to prove by going forward again. So let's do one of those reverse ones.
Okay.
Okay. And let me save the file first. This way I won't forget to do it later. All right.
Reminder which one. Let's go.
Okay, so these are the 3 lines that we want to, deal with. And let's just say this is one of those questions where the post condition is given to you, and you have to figure out what is the pre-condition. So we'll just say the post condition is x equals 22 and y equals 44 and z equals 22. Okay. What is pre1? That's the question. What do we know for sure before line 1 executes? That's basically what I'm asking. All right. So going backwards, I'm going to change the format of the question so that you don't have to show me the steps of going backwards. But since I am teaching the class, I have to show you how I go backwards step by step.
What does that mean exactly on the test?
What do you want us to write?
Yeah.
You don't have to write anything for the steps going backwards, but you do have to state what your pre1 is, and then you have to prove that based on your pre1, you have to be able to get back to post 3. Yep.
So we find pre1 pretty much shorthand and then write it back to the.
Then you have to follow all the rules in the homework assignment to
post
go
back.
forward again. Okay. So let's say pre3. So what do you think is pre3? Knowing that post 3 is x equals to 22 and y equals to 44 and z equals to 22, what do you think is pre3? Yep.
We don't know what z is.
Exactly. What about the rest?
The others are true.
Okay,
X
so we
is
can keep
22.
we can keep these two. Okay, very good. And then we know post2 equals to pre3 because lines 2 are sequential. Okay. Yep.
Do we need to state that last line in the test?
No, because remember in the test I don't need you to show the steps going backwards, but you have to go forward again, and that's where your points will count. Save the document. Okay, and now we have to figure out what is pre2. We know what is post2. Post2 is we know something about x, we know something about y. So what do you think is pre2?
We're going to forget y.
We have to forget what we know about y because
Y is being assigned.
y is updated by an expression that is not reversible. Okay. So post 1 is the same as pre2 because lines 1 and 2 are sequential. And how do I derive what is pre 1? What do you think?
X equals 11.
X equals 11. Very good. Okay, so now we have a pretty good suspicion that pre 1 is just x equals to 11. Now you have to go forward again to prove that that will in fact get you to the post 3 that we started off from. Yep.
Now we'll say X equals question mark, Y equals question mark. I mean, Z equals question mark.
No, we don't use the question mark. If you don't know something for sure about a variable, we just don't say anything.
Okay.
In other words, in this case, we only know for sure that x equals to 11, so that's the only thing we can state as the precondition of line 1.
Okay.
Question? Okay. So now we have to go forward again. And to go forward again, we have to deal with line 1. And line 1 is an assignment statement, which means you have to answer this question first. Does the right-hand side refer to the left-hand side on line 1? The answer is yes.
Yes.
Okay. The right-hand side, f of x is 2x, is it reversible?
Yes.
Okay, so we'll say it is reversible. And the inverse function is what? Go ahead.
Well, 1/2 x.
1 divided by x. Okay, 1/2 of x, same thing. Okay, very good. So then we can use the substitution rule. Yep, go ahead.
I just have a question. Instead of using that prime of x, can you use the small f of x and big f of x? Capital F of x? Or is that pretty complicated?
If you make it clear that the inverse function, big F of x, then I can accept that.
Okay.
But if you don't mention anything, then I cannot associate your big F, or uppercase F of x being the inverse function. So you do have to make it clear if you don't use the convention. Okay. Then we have to use the substitution rule because the answer is yes to this question, and also the function of the right-hand side is reversible. To use the substitution rule, now this part you have to pay attention because I'm going to expect the same format from your answer. You have to say post 1 equals to the substitution operation applied to pre 1. We look for the variable on the left-hand side, and then we replace it with the inverse function applied to that variable. So this is basically the same thing as in a homework assignment. And then in the second line, we expand this. Okay, in this case, it's not too bad. X equals to 11 is the only thing we know about in pre 1. And f prime of x is just x divided by 2. And then we carry out the actual substitution. It becomes x divided by 2 equals to 11. Or if you prefer, the parentheses arranged like this. That's it, okay? We don't need to do any more simplifications at this point. Any questions about the first step? The second step, pretty much the same thing, except the answer to the question will be different. Does the right-hand side refer to the left-hand side on line 2? The answer is no.
Don't
So we have to use the forget rule. Yep.
don't we have to write pre-2 as post 1 because they're sequential?
Oh, that's right. Yes, we have to do that too. We can do it here. So we have to say pre2 equals post 1 because lines 1 and 2 are sequential. And then we have to apply the forget rule. The forget rule says post 2 is the result of forgetting something in pre 2. something that mentions which variable in this case. Let's go back and take a look at the code. Something that mentions y, okay? And after this, we also know one thing for sure. We know that x equals y after that. Oh, no, 2x. Okay, if you want to be explicit, you can specify x 2 times x. If you specify 2x, that's fine. I can read that expression just as well. Are there any questions at this point? Then the next line is just expanding what is in pre2. Pre2 has x divided by 2 equals to 11. And the only thing in pre2 does not contain references to y, so there really is nothing to forget in this case. Now I know that we can actually do some simplification here, because from here we can actually resolve and find out that x does equal to 22, and from here we can find out that y will equal to 44. But there's no need for you to do the simplifications. Okay, you can leave it just the way it is like this. Yep.
Okay, on line 32 you say forget x divided by 2 equals 11. Why?
That's your post 1, and your pre2 is post 1, and you have to put a pre2 here, and this is your pre2. Okay, let's go step by step. We know that pre2 equals post 1, don't we?
Right.
And post 1 is this, right?
Okay.
And since pre2 equals post 1, pre2 is this as well.
Okay.
And pre2 appears here, and all I'm doing is to substitute pre2 with what it is, actually.
I think you should say define what pre1 is, because substitute, you can use a substitute rule.
What? Sorry?
So if you're actually defining the pre2, what pre2 is, same thing as post 1.
Yes.
So you're just defining what it means, basically, what it is.
I am reasoning out, what pre2 should be. Yep, correct. I'm not defining it. I'm just, saying what it is. I'm deriving it. Right. But there's a difference, because when I define something, it seems like can be arbitrary. But when I derive something, it is not arbitrary. It is the result of applying the logic to what is already given to me. Okay. Are there any questions about this? The last step is pretty much the same thing. The last step is you ask the same question. So for the most part, I can copy and paste it. But when I do this, I have to be careful and change all the references to line 3. So we have to change this to line 2. Pre3 equals to post. Pre3 equals post 2 because lines 2 and 3 are sequential. And then post 3 is forget something in post 3. Anything that mentions z in this case needs to be forgotten. And we also, after this, z will get the same value as x. And here we have to remember the other part of pre3, which also does not mention z. And this part has to be changed as well to z equals x.
Can you change the y on line 41?
Sorry?
On line 41, you forget y.
Oh, yep. You have to change this to z. But you won't have this problem because you're not going to copy and paste. Unless someone brings in a little hand scanner and a little hand printer. So that's it. Okay. Now I know it doesn't look like what it started off with, but when you apply the actual operation, it will be the same. Because this one here, you can multiply both sides by 2, then it becomes x equals to 22. Knowing that x equals to 22 and z equals to x, you can also conclude that z equals to 22. But knowing that x is 22, you also can conclude that y equals to 2 times 22, which is 44. But you don't have to do that. Okay, that's one step that you do not have to apply, because I cannot assume that you can do the algebra, for in this case to simplify it. So this is fine, as a correct answer. Okay, so yep, go ahead.
On line 41, don't you have to have a z? Forget x over 2 equals 11,
right here.
comma z.
Yep, it's right here, comma Z.
Why not on the first part? That's what's confusing me.
This entire part is your pre-3. Oh, I see the parentheses are not matching, so I'm missing one. Okay, pre-3 is the same as post-2, which is this expression. And that entire expression takes the place of pre-3.
Right.
So this comma X is still here. It is preserved, over here too.
But why are you saying
Sorry?
why are you saying forget that when we're retaining that? That's what's confusing me. We're
Because we
retaining
are
that, but we're forgetting Z.
We are forgetting everything in pre-3 that mentions Z, and this is pre-3. So it is redundant. There's nothing to forget, but I still have to state it so that I know what the components are, and then I can say, oh, by the way, there's nothing to remove.
Both are
and
in
as a result,
relation to Z, right?
What?
Right there. That whole line, both are relating to the Z, right?
You mean this line here and this line here?
No, forget on the 41, that first half is all relating to Z. Both the X over 2 equals 11 and Y, right?
This part?
Yeah.
No, that's our pre-3. That's our precondition of line 3.
That's relating to Z here.
No, this is what we know before line 3 executes.
Okay.
And our job is to forget any component that has any mentioning of Z, but since it does not, then we can preserve the entire thing.
Okay. I've just wrote it down. I'm just going to copy exactly like on the test, right?
Well, you kind of have to understand why that is the case, too.
I'm trying to.
Okay. Yep.
Would it be okay to, I've been writing left-hand side refers to right-hand side. Would that be wrong? Since
That would be wrong because the left-hand side is a single variable,
Right.
but the right-hand side can be a long expression. So you still have to refer to it as the right-hand side refers to the left-hand side.
Okay.
Okay. Any other questions? Yep.
On the test, are you gonna give out the definition, like give a word, vocabulary, and define this word?
No. Nothing simple like that. That's against my principle, asking questions that requires memorization. Okay. Any other questions? No? No questions? All right. So if there are no questions, we are moving on to structured programming or hierarchical structures, top-down design. There you go. All right. So the first part of this module talks about, what is top-down design. And typically, I give you a few live examples of what is top-down design and why it is important in daily life, not just in terms of writing algorithms, but also in other things that you have to do on a daily basis. Okay, are you guys doing okay? All right. Okay. You're still explaining the
Yes.
forget concept?
Yes.
Okay. Can you wait until after the class, maybe? Okay, so you might want to write down your question first, so that you don't forget, but let's do it after the class. Okay. All right. So, I know it is important to answer those questions, but at the same time, if you don't pay attention, you will miss this part too. So we want to make sure that we don't miss this part. Okay, let's go to maps.google.com. Okay. Where's Sacramento? Okay, why can't I find Sacramento on this map? Well, I can. Okay, where's ARC? Where is this classroom on this map?
Under that Google Doc.
Okay, but it's not captioned. Okay, why is it not captioned? Why can't I see room 121 of ARC on this map?
The scale is too small.
The scale is too small and the resolution of the projector is limited. Okay, let's just say that I give you a magical projector that has an infinite resolution. In other words, I can make the dot on the screen as small as it needs to be so that I can put in like tiny little writing on it. Okay, so would that help?
No.
It wouldn't help because
Couldn't see it.
it will be too small. And guess what? If I can show room 121 of ARC, guess what else would pop up?
Everything.
Room 123, room 122, and all the other colleges, everything will show up. So even if the screen has the resolution to do it, can you find it on the screen?
No.
Where in the world is room 121? Right? Sorry?
Magnifying glass.
Magnifying glass. Okay. So how many things can you handle, or how many things can you spot and read and search for right away on the screen at any particular time? Let's say it's not something that you're already familiar with. Well, this is something that you're familiar with, so let's go switch to something that you're not. Where is the Sichuan province in China?
Right about there.
Somewhere.
It's right there.
Okay.
Over there.
So the question, the point is, okay, let me see. There we go. That makes it a little better. But even so, it's not that easy, right? It's because we can only track so many things at the same time. I mean, that's just our mental capability. How many things can you track at the same time, assuming it is not something that you are already familiar with? 7, 8 at the most, somewhere around there. Okay, so that's why we don't want to display everything on the same screen. We only want to display 7 or 8 items at the same time. Another example of top-down, or why we need to only present a few items at a time is easy. That one you already know. We talked about that already. It has to do with your file system. Okay. In other words, what if I tell you that your new 2 terabyte hard drive, new file system from Microsoft, only allows you to put everything in the root folder or the top level directory? You still have the 2 terabyte. You still have the same 2 terabytes. But how are you going to organize your files?
Get creative with naming.
You have to get creative with the names and a good memory to remember that how creative you were, right? You have to be creative but consistent at the same time to do it. How many files do you typically store on your 1 or 2 terabyte hard drive? Even if you have movies, okay, even if you store just movies on the hard drive, it will still be thousands of movies, or at least hundreds of movies. If you don't have a way to organize it systematically, it will be pretty hard to locate a particular movie or a particular file. Now, movies are pretty big files. They're 4 to 8 gigabytes each, assuming you don't re-encode everything. Think of all those little files, all your digital images from your digital cameras. Okay, how many pictures can you fit within a 2 terabyte hard drive? Lots. Okay, even if you have a 20 megapixel camera, you can still store a lot of pictures in raw format. Okay, so that means organization is the most important part. When you have that many files and a huge capacity, how do you organize your digital pictures? I just throw everything into one big bin. Yeah, go ahead.
By date or whatever?
By date, that's the most, the common one, the most common method to organize your pictures, because when you upload your picture from your camera to your computer, you're uploading it on a particular day. So you can just record what day you upload those pictures, but within those pictures, you can still have, pictures of different sorts. Family reunions, okay, trips that you have taken, hiking trips, backyards, your accomplishment, all your tomato plants and stuff like that. So it's still a big mess, to organize, but at least you can organize by the date. It's the same thing with programming. Okay, if you write an algorithm that is, say only 500 lines. Okay, let's not talk about thousands. Let's talk about only 500. When you list or when you print out that algorithm, how many physical pages is it going to fit? Assuming the standard is we can fit 66 lines on a page.
About 8.
About 8 pages. Yep. So if you have to look for a particular thing, or if you want to trace the algorithm, how are you going to do that? You find the end while on one page. Where's the while, matching while, of that end while? It may be a few lines above if it is like really nested into it, it may be 4 or 5 or up to 8 pages, before that. So tracing that algorithm becomes a big hassle. What about debugging the algorithm? It's a nightmare. I can tell you that because I have done it. I'm not the person who wrote the 500-line algorithm. I'm the poor person who's responsible to debug it. Guess what happened to it? Yep, it finds its way into the trash can, and I just rewrote the entire algorithm using my way. Okay, that's the only way to do it. That's the only practical way to deal with something like that. Okay, because I cannot keep track of all 500 lines, at the same time. And guess what? It has the taboo word, the G word in programming. What is the G word of programming? Go to. Exactly. It has go-tos all over the place. Okay, so it was a big, huge mess, and I just had to rewrite that. All right, so I think we have just understood the reasoning of why do we want to look at things from a top-down view, and why we want to organize everything in a hierarchical fashion. Hierarchical simply means that you have layers and layers of stuff, just like your folders can have folders, and your folders can have folders, and you can do this until like 6 or 7 levels down. Then you can have your regular files. And in here, in section 3, we talk about top-down design for algorithms, and there are specific considerations when you do it in a programming setting. In a programming setting, I'm just jumping to the point here. You might want to make sure that your algorithm will fit on screen. You can display the entire thing at once on screen. Why would I do that? Why can't I just have a maybe 100-line algorithm? I just have to page up and page down to see the whole thing. Go ahead.
I would get lost.
It will be difficult to track, right? I mean, if the longer the lines, the lengthier the algorithm, the more difficult it is to track it, when you try to debug it. So we want to limit that to about 40 lines or so at least the entire algorithm can show on the screen all at once. So that way you don't have to page up and page down, and that saves you some trouble already. And this part also depends on how comfortable you feel to displaying 40 lines of code all at once on the screen. It depends on your screen size, your eyesight, and many other factors. For beginning programmers, I would recommend about 20 lines. Okay, basically you want to make that number smaller and smaller just so that you can keep track of everything in that algorithm at any particular time. Great. So we don't want to write any algorithm that's more than 20 or 40 lines. How many lines of code do you think is in, let's say, Microsoft Word? 40 lines? 400? Maybe 4,000?
One really long.
I would imagine the magnitude would be around 4 million lines maybe, okay, for Microsoft Word. So how do we turn 4 million lines into 20 or 40?
Divided by a million.
Good calculation.
It's the same way as you organize your pictures, okay, your files in your file system. You use, you basically put 20 items into one folder, and then you put the next 20 items into the next folder, and then you have 20 of these folders that you combine into one parent folder. And then you have 20 of those folders that you combine into another level of folder, and so on and so forth. Yep.
While you have all those folders, do they after it's all done, do you get rid of the folders and then it's just all straight code or something?
Nope, you don't get rid of the folders because you don't want to turn your hard drive back into one single folder, do you?
So that's how programmers find something in Word, like when they're debugging, what folder the problem would
Right.
be
We have
or something
specific.
like
We
that.
have a special name for those folders. They're called subroutines. We'll talk about that later. But right now, we are just talking about the organization of the program. We need these organizational units so that each unit only has to handle about 20 to 40 items. Okay. Any questions at this point? No questions? All right. Well, let's assume that we can only have 20 items in each container, and we have 4 million of these items to handle. The question is, how many levels of these containers are we talking about? Let me show you the picture. Okay, at the top level, we have 20 of these things. Okay, each one of these things has 20 of something else. Each one has 20 of something else. So the question is, how many levels are we talking about in order to contain 4 million items?
4 million equals.
In other words, I'm asking 20 to the power of what equals to 4 million, or approximately. What is n? Yep.
7?
I don't think it would take 7.
Oh.
Because this is million, which means even if this is 10, it will only take 7. But if it is 20, it will take less than 7 levels. I would think it's about 5 or even less. Let's find out. Let's see, do I have a calculator? I don't have an actual, oh, I have a fancy calculator. What are we talking about here?
6.
We have a spreadsheet. That's the fanciest calculator ever. Okay, so we are talking about the log of 4 million divided by the log of 20. So the answer is about 5 levels. Okay? It's not much. If you think about it, that's not much. You have 4 million items, and all you need is like 5 levels of these folders, each one containing 20 items, and you can handle the 4 million items. Any questions about this?
Yeah, but every level has a,
Sorry?
But every level has its own 20 files, so
Yes.
it's still a lot.
It's still a lot, but in terms of how many levels of folders you have to go through, it's not that much. It's basically a folder in a folder in a folder in a folder in a folder. I think if you look at your file structure at home, you can easily go to like 8 levels already. Right? If you try to locate one of your files in your My Documents folder, many times from the root of the entire drive, you probably have to go through at least 6 to 7 levels to get to your own files. So 5 levels is not much. Yep. I'm not taking row today. And I won't be taking row on Thursday because I can just count who turned in the test. Oh, since we're talking about the test, I have to say, I'm observing something that's interesting regarding homework assignments. I have seen, homework assignments that are not really well done. Then I look up, the activity of, that person, and that person logged in very sparsely, and for the most part, most of the topics have not been even looked at. That's consistent. I look at some homework assignments, it's well done. I look up the activity of that student, and that student has checked out every single item on the list, revisiting topics a few times. That's consistent. I have also seen homework assignments, not just one, but all the homework assignments that have been turned in. They're all perfect scores. I look at the activities. Very few of the topics have been clicked. I can understand the first few topics are just fairly easy stuff and people don't have to click it, but the pre and post conditions, that's not easy. And yet the homework assignment is like 100%. That's not very consistent.
You study from your notes.
Hmm?
You study from your notes.
Well, these notes require you to click on something in Moodle. That's the YouTube, okay, that's the YouTube, but the YouTube kind of zips by because I don't really read my notes, in my classes. I assume that you have read it already before the class, so I just kind of zoom through a lot of this stuff here using live examples. So I'm looking for, so when I collect results from the exam, I'll do the same thing. I'll do a little bit of analysis and try to spot things that are out of place. In other words, I'll be looking for something like homework assignments, close to 100%, test is down to 20%. That would not be consistent. I understand a lot of people do not do as well in an exam. Okay, so I know that most people would can get 100% in the homework because you can spend all the time that you want, that you need on homework. But in the test, you are kind of in a rush. So most of the time you will get not perfect scores, but still pretty high. Okay, but if I'm looking at a ratio that is way too extreme, let's say the class average of that ratio is about, let's say, 75%. Okay, so on the average, someone who gets 100% in a homework assignment will only get about 75% in a test. I'm just making a number up here. If someone is getting that ratio all the way down to 20% or 10% or 15%, that's going to flag me that something is inconsistent. Okay, so I'm going to look for stuff like that in the exam too. Would it be unreasonable for me to do it? I mean, I'm not going to use that and just and accuse someone of cheating, but I'm going to kind of take notes of that and see if there are other factors that other things that I can see. All right. So getting back to the notes here. So the question is, how do we fit fit 4 million items into just folders, and each folder can only hold 20 items, and that's the answer. Okay, we just have levels of hierarchy of these folders. And here we have an example of factoring. In fact, this is a good exercise because we are going to write our very first algorithm using the concepts that we have learned so far. We have variables, we have assignment statements, we have conditional statements, and we have loops. Okay, we have all the pieces that we need to write an algorithm to factor a number to its prime numbers, to its prime factors. But before we do anything like that, it is always helpful to remind ourselves how to do it by hand. If you cannot do something by hand, what are your chances of being able to tell the computer how to perform that job? Just do it, right? I mean. So it is helpful for us to go through a few examples. Okay. Now I can go through examples like something that's simple, like starting with 6. How do we factor 6 into its prime components? All of you will say, "Oh, that's easy. It's 6 is 2 times 3, and we are done." Okay. So that means what this means is it's not useful to use simple test cases, because with simple test cases, a lot of times when we go through that in our head, we use what I call the eyeball algorithm. The eyeball algorithm simply means that when you look at the problem, you instantly figure out the answer without having to apply any type of systematic logic to it. So we're going to try something different. We'll try something like, well, let's see. Would this be difficult? That's not difficult. That's not difficult because we are still going to apply our rules of thumb, heuristics. What is the rule of thumb that will tell you at least one of the factors of 116? Is divisible by 2 because the last digit is divisible by 2. Okay, let's try something harder. Oh, this is harder. Is it?
It's divisible
It's a
by
little bit
3.
harder, but we know right away it's divisible by 3, and why?
Oh, I was going to say divisible by 1.
Because all the digits add up to 3. Or add up to
Exactly. When you add all the digits, that number is itself divisible by 3. Okay, so these are all the heuristics that we can use to quickly figure out at least some of the prime factors. So when you're testing, it is always helpful to test you with something that is a little bit harder. So how about that? That seems harder. Again, we have another heuristic. It ends with a 5 or a 0, so that number has to be divisible by 5. All right. Is that a little harder now? It's still divisible by 3, isn't it? And how about that? I think that's a good number to try. I'm just pulling this number out of thin air. Okay? All right, so let's try to factor this number. How do you do it? Okay, how do we factor a number like this? Well, let's just say that TAC is not very bright. And, I would try all the possible prime numbers. Yep.
We can rule out 3, 5.
We can rule out 2,
3,
3, 5,
2.
and probably 11. I don't know. Let's try it, okay? So let's just say that TAC is not very bright, but he's very systematic, very consistent, okay? And I will say, okay, I'll try it with 2 first, okay? And the result is it's going to have a remainder of 1. It's going to have a non-zero remainder, okay? Is it wrong for me to try 2 as a prime factor? In other words, Is it possible for me to misidentify 2 as a prime factor, even though it is obviously not?
No.
It's not, okay? Because when I try something like this, the remainder is going to be non-zero to confirm that 2 is not a factor of this number, right? So I can be slow, I can be dumb, but I'm not wrong. Okay? Now that is going to be a very important factor when you write algorithms, okay? Because when you try to encode everything that you can do by hand, sometimes it's not so easy, okay? What about this? It's not very smart because if you add up all the digits of this number, that number itself is not divisible by 3. So we can actually use our heuristic to figure out that this number is not divisible by 3. But is it wrong for me to do something like this? Can I accidentally identify this number as a number that is divisible by 3? No, it's not possible because the remainder is going to be non-zero. Okay? So I don't even care what it is, I just say it is non-zero. Here comes something that is even number. Okay? I will even try that. I mean, tag, that's just way dumb, right? I mean, if I know that 2 is not a factor, trying 4 is just not very smart. But once again, I don't care about being dumb and being slow. I only care about, am I correct? Can I accidentally and incorrectly identify 4 as a factor of that number? No, because the remainder, once again, is going to be non-zero. Very good. Okay. And I'm going to try, the other numbers. 5 is blah, blah, blah. And once again, it is not smart, but not wrong either. Okay. And so on. Okay. Now, even though I'm slow and I'm not very bright, I have access to a spreadsheet. So what I'm going to do is to say, okay, this is the number that I'm considering. So let me switch that page. 116169, 116169. Ah, no.
Uh-oh.
Okay, 116169. And I will list all the numbers here, or at least a good portion of that. And then I will say, go ahead and find the modulus of this number. So we'll go by the dividend.
It's not the same number.
It's not?
It's supposed to end in 5 original. That's right. Or 7,
116159. Oh, okay. Let me close this one first. This is distracting me. Okay. And I have to remember to save it occasionally, just in case I forget to do it at the end of the class. Okay. All right, fine. Okay. Made a big difference. Okay, so what I can do now is I can say the divisor, which is, the dividend, sorry. The dividend is going to be B $2, which means it's not going to change as I do something like this. Well, so far we haven't found anything yet.
It's prime.
It's prime. It's prime? Not yet. Not yet. Not yet. And so on. Okay? I have no idea when I will actually find a prime factor. It may be a prime number, it may not be a prime number. We'll figure out whether it's a prime number later. But let's just focus on this spreadsheet here. What is this spreadsheet doing? This is the number that is in question. These are the potential factors of that number. And this is the remainder of the division when I divide 116159 by the number on the column on the left-hand side. Okay? And some of you will say, but that's not very smart, because we, for sure, using rules of thumb, we could have ruled out this, and so on. In other words, I could have just tried it with all the non-obvious prime factors, because the obvious ones I could have skipped, right? That makes sense. I could have made it faster by skipping that. Now the question is, but that's going to complicate my algorithm, isn't it? Okay? how are you going to encode the logic of, oh, if the last digit is a 2, it has to be divisible by 2. Or if the last digit is an even number, it has to be divisible by 2. First of all, what is the base of the number that we are talking about here? Base 10, right? But what do you think numbers are, how do you think numbers are represented inside the computer? It's in binary, okay? So in order to apply the heuristics that we use, every day, we have to first convert the number from a binary representation to a decimal representation. Then we have to do all the summation of the digits and then see if that is divisible by 3. That's really not easy. Okay, it really complicates the logic and it wastes time too. This way it is fairly easy. The algorithm is very simple. Okay? Are there any questions about my approach of doing things? It's not the fastest way, it's not the most efficient way, but it's very systematic. And it is guaranteed to be correct because there's no way I can misidentify a number as a prime factor when it is not a prime factor. Is that okay so far? Because we want to make sure this approach is not incorrect first. It may be slow, it may be inefficient, we can optimize it later. But first of all, we want to make sure it does not give us a wrong answer. Okay, so we can extend this a little bit further, but since most of you are convinced it's a prime number, it probably is a prime number. We'll see. This is hard to see too, so we'll see, we'll say if this number equals to 0, say found it, otherwise say nothing.
That's hard.
Oh. Okay, so we just have to look for found it. Not yet. And how far do you think I have to go?
Up to halfway.
Up to halfway. Why not 1 to 1/3 of the way, or 1/4 of the way, or square root of the way?
Question.
Okay, so we'll talk about that too. Okay, so effectively, basically what we have to do, let me find the square root of this number first. So we'll say square root of this number. Once we get to 340 and we cannot find a factor, I can confirm the number is prime. Okay, so that's a really good shortcut, isn't it? Oh, and we already got past that point. Okay, 340 is right here, and we cannot find a factor even up to that point. Okay, so at this point, I know this number is prime. So I will show you why I can make that observation. Is it wrong if I keep going? In other words, let's say I don't know this trick, and I'm going to extend this table all the way to 116159. Would that be wrong?
No.
By extending the table, would I accidentally recognize a number as a prime factor when it's not? No. So that's still kind of easy. Okay, it is wasting time, but it is not incorrect. So we'll stick with this approach, and I'll just use the ... here to represent all the other numbers that we go through. And the last number we're going to try, let's just say that we're not going to be very smart. This is $2, so we'll say $2 minus 1. This is our very last number to try, and the remainder is 1. Okay, obviously this is not very smart, but at least it is correct. All right. Let's write an algorithm to do this. Do you think this is a fairly easy way to encode in an algorithm? Okay, what is involved in this case? Do you think it involves some kind of repetition?
Yep.
I sure hope that you can see that it involves quite a bit of repetition here. Let's go ahead and write the algorithm. So the way I do is, or the way I do it in this class, is when I write an algorithm, I don't give you the entire algorithm to begin with. I first ask you, does it involve a loop or a conditional statement? as the overall logic.
A
A loop. Okay, so we'll do it like this. So we'll say, version 1 of this algorithm is loop and loop, and we're done. Whoa, that's too easy. Okay, because the first thing we want to do is just to recognize the fact that it involves a loop. Great. Now, every time you have a loop, most of the time, you want to make sure the loop does terminate at some point. Okay. So let's say when we are going to exit the loop. When do we get out of the loop? In other words, if you switch back to the spreadsheet here, when do we get out of doing this repetitive thing?
When remainder is 0.
When we find a remainder of 0. When we find a number where when you divide the dividend by that number, the remainder is 0. Okay? So let's just say that we don't want to be very clear at this point. We'll just say that when the remainder is 0. Okay? We're not even sure what remainder of what. Okay? But we're just doing it step by step. Okay, in version 3, we want to be a little bit more clear. In other words, we want to be able to refer to the dividend, the number that is in question, and also the potential factor that we are dealing with. Okay, so we are starting to use variable names in this case. So when you do something like this, then you'll say, okay, let n be the number in question to be factored. Okay, any question about this? In other words, I'm just being lazy. Instead of saying the number to be factored, 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 I'm just saying it's n. A whole lot easier. Okay? And I'm going to say let f be the potential factor of n. So instead of saying the potential factor of n, the potential factor of n, the potential factor of n, I just say f. Okay? A whole lot easier. Now, given these two names, can I be a little bit more clear about the exit condition of the loop?
Yes.
Okay, so we can say when the remainder of n divided by f is 0. Okay, now our exit condition is actually not quite right yet, but it's fine. Okay, we'll handle that later. Oh, okay, but since we do it this way, I have to finish this sequence with one last step, because we will find that factor. Right? The loop has to get out. This is how we're going to get out of the loop. When f becomes n, then we know for sure that the remainder of n divided by f has got to be 0. Does that make sense? Yep.
You could have an or there when remainder n divided by f equals 0. Or?
No, we don't need an or. We're trying to keep the logic simple at this point. Okay. So is this making sense? Okay, is this okay so far with version 3? Okay. Let's take a look at version 4. Version 4. Okay. Version 4 is to be more clear about how do we get these values f and n and stuff like that. Where do we start with f? What is the first number that we try out? Yep. 2. Go ahead.
I was going to say integers.
Integers, but which number do we use first? In other words, if you switch back to the spreadsheet, we start with the number 2. Can I start with some other numbers? I could have, okay?
Not advisable. Not advisable.
Not advisable, because if I start with a composite number, then it is potentially possible that I can misidentify a composite number being the prime factor of the number. So it is always good to start with a smaller number and then move up. Okay. How can I do that in the algorithm? How can I make sure that I start with 2? What about I just say that before the loop? Now, if I do this before the loop, what do I do when this condition is not true? We have to increment f by 1, right? Because according to this spreadsheet here, If 2 is confirmed not to be a factor of this number, we move on to 3. When 3 is confirmed not to be a factor, we move on to 4, and so on. So every single time we just increment. To increment a number, we just say f gets f plus 1. Is that working out so far?
No.
No?
No, because when you run through that iteration, the first number you're going to run into is going to be 3.
Ah,
before it checks it.
but that's okay because we don't really have a construct called loop and loop. So when I say loop and loop, all I'm saying is it is some kind of iteration, but I have yet to determine whether it is a while loop or a repeat until loop. In other words, we have not determined whether this is going to be a pre-checking loop or post-checking loop. All I know is this is some kind of a loop, and we also know that to get out of this loop, we need the remainder of n divided by f to be 0. Okay. So that's a good point. That's a very good point, but we'll resolve that later. Okay, very good. So you can see how we gradually increase the precision of the algorithm. Okay, we start with something that's truly vague. It's just a loop, and then we add something to it. We add some more to it. We add some more to it. At this point, I can be a little bit more concise about the operator. When I say the remainder of n divided by f is 0, I would just say that when n mod f equals to 0. In other words, I am introducing a new operator called mod. Okay? When you use n mod f, all it does is to give you the remainder of n divided by f. Okay? The mod operator is basically the same as a division, except it doesn't give you the quotient of the division. It gives you the remainder of the division. What is 5 mod 2?
1.
Okay, very good. What is 7 mod 2? 1. What is 12 mod 5? 2. Very good. So you guys have a pretty good handle on the mod operator. It's the same as a division, except it doesn't give you the quotient. It gives you the remainder. All right. So we just made a, one little refinement. And now, to get back to your question, we have to say, but Tech, there's no such thing as a loop and loop. We have while do, we have repeat until. So which one should we use? Well, that's a tricky question because we could have used either one. In other words, we can use, okay, this is version 5a, which means it's one of the alternatives. One of the alternatives is to use a while loop. So we can say while. What should I say when I convert it to a while loop? Remember, while is the same as long as. In other words, we are stating the condition to stay in the loop, not the condition to get out of the loop.
And mod f not equal to 0.
Very good. Okay, so we'll say when n mod f does not equal to 0, do, and the rest is the same. F gets f plus 1. That's it. That's version 5a. But there's also another version. Version 5b. Version 5b is going to say f gets 1 to begin with, and then we can say repeat f gets f plus 1 until n mod f equals to 0 in this case. So these two are equivalent. In other words, they are both correct. The first one will start with a value of 2 in f, but because this is a pre-checking loop, I am checking whether f is a prime factor when it has a value of 2. That's the first value that I will check. The second one is a post-checking loop, but I start with a number that is 1 less than what I really want to use. So it has to go through this step here because it is a post-checking loop. I have to go through the body of the loop at least once. So by the time I get to the condition, f will have a value of 2 already. So I still end up with testing it starting with a value of 2. In other words, in this case, I could have gone with 5a or I could have gone with 5b. One is better than the other one, even though they are equivalent. Which one is better?
The pre-checking.
The pre-checking one is better. Why is it better?
It's less operations.
It's fewer operations, but also to the programmer, why is 5a better?
There's no inferring.
There's no inferring. Very good. Okay, Because when you look at line 97 in the text file, it is very clear. We start with 2. Whereas with 5b, it looks like we're starting with 1. Then you have to figure out, oh, this is a post-checking loop. By the time we get to this statement, it will have a value of 2. That is much less direct than the first approach. If an approach is more direct and it gets the same thing done, you always go with that. And that's why in this case, 5a is not only the correct answer, it is also the better answer out of these two. Most of the time in programming, you can probably do something like this to convert a pre-checking loop into a post-checking loop, but that would actually make it more complicated to understand. So if you can get away with a pre-checking loop without complicating the logic, go with a pre-checking loop. All right. So how would you describe algorithm 5a? Well, 5b has the same thing, but let's just say that we want to describe algorithm 5a. How would you describe it? In one phrase, how would you describe it? Factoring. It's not quite factoring because it only finds one single prime factor. Factoring means, you look at 8, you have to break it down to 2 times 2 times 2. 2 times 2 times 2, yeah, 3 times. Okay? So this is not quite, factoring, but it is one important step in factoring. How would you describe it?
It's looking for one factor.
We're looking for one factor, okay? But when you describe it, you should also mention the variable names so that you can relate the algorithm to the specific variable names that we are using. How about this? Find prime factor f of n. Would that be okay? It's descriptive enough because we are relating the two variables and we are also stating what it does. It only finds one single prime factor and put it into the variable f, and we are finding that prime factor of n. Okay? Now that we have this little tool here, we can try to think about, but what about factoring the whole number? Assuming that we have this available to us already, this is something that we know how to do. What do we do when we start with a particular number? Let's say, this time we can pick something that's not as difficult as the other one. Let's try 115. Okay, how do we factor 115? Well, we have this approach already. So the first time you apply this approach, what are we going to find as the prime factor? 5, okay. So this is 5 times what?
23.
23. And when you apply this to 23, what do you find?
Prime factor.
23 itself is prime, but we still want to use the same approach and say 23, okay. We say 23 is 23 times 1, okay? In other words, this is the result of applying this method on this number. Okay? This is the result of applying this method on this number, and this is the remaining portion of that number. Are we done yet at this step? Yes, we are done, because we are now down to 1. Is 1 a prime number?
Yes.
No. By definition, it is not. So if you look up the definition of a prime number, it says it is any integer that is divisible by itself and 1 except for 1 itself. So 1 is not a prime number. Okay? So by the time we get down to 1, we are done. Okay? Let's try something else. Let's try 54. Okay? 54 is going to have a few lines here. When we apply this method, which prime number is it going to find? 2. Okay, so it's 2 times 27. 27 is 3 times 9. And 9 is 3 times 3. I'm not done yet because I still have a number of 3 to factor. So now I have to say 3 is 3 times 1. And now I'm done because the number that I have to factor next is 1, and 1 is not even a prime number, so we are all done. Yeah.
What happened to the 2?
The 2 is handled here. first line handles the 2. Okay? So now the question is, how do we write this algorithm? First of all, is it repetitive?
Yes.
Okay, very good. So let's start with the same thing again. Version 1 is just loop and loop. Version 2, loop and loop when what? Exit the loop when what? When the number to factor is 1. Is that okay? I mean, that's consistent with our example done by hand. Version 3. Version 3 is, well, let's give it some variables so that we can refer to what is the number to factor and so on. So we'll say n, let n be the number to factor. Let f be a prime factor of n. Okay? With those two variables, how can I change the exit condition? That should be a pretty easy thing to do. Yeah. Okay. Pretty easy. All right. So now we have to think, how is n going to get to 1 when it starts off with 54 or 95 or something like that? What do we do in the loop to reduce the value of n? Well, remember one thing. Why do we even bother to go through this trouble to find out how to find the prime factor f of n? Because it's a step of doing the factoring. Okay? What do you say that we apply this first? First thing in the loop, we do this. In other words, we start with an n that we are supposed to factor, and the first thing we do is we find a prime factor f of n. The next thing is, well, let's tell the end user what f is, okay? Because otherwise, it's pointless to find a prime factor. What do we do next? In other words, we have to get n somehow down to 1 eventually so that we can get out of the loop. When you look at our example by hand, this is n. This is n in the second iteration. This is n in the third iteration. This is n in the fourth iteration. And n eventually becomes 1. How do we get 54 down to 27? And 27 down to 9? Yep.
Divide by a prime factor.
Divided by the prime factor. Okay, so that means n gets n divided by f. Right? Are we done? We're pretty much done. Okay, so version 5 is to figure out, okay, should we use a pre-checking loop or a post-checking loop? What do you think? We could get away with a pre-checking loop would work as well. Okay, so once again we have 5a and 5b in this case. So 5a is, we can say while n does not equal to 1, do. And this is the way I write my programs too. When I actually write programs, I always end the construct immediately and then go back to fill in the content of that construct. This way I won't forget. It also makes indentation matching a whole lot easier because you're doing it right away. You can match the indentation right away. But if you try to do it at the end, sometimes you will find it very difficult to do all the matching and the indentation. So now we can say we just stash everything here into the content of the loop, and then we're done. Version 5b is about the same thing. It's actually easier because all I have to do is to change loop and loop to repeat until. Like that. In this case, it's much harder to say that one approach is better than the other one because they are really the same. Okay? In this case, they're really the same. The only difference in this case is whether someone can try to trick your algorithm by making n equal to 1 to begin with. Okay? If someone gives you n equal to 1 to begin with, which one will not give you the correct result? 5B is going to be in trouble, right? Because if you look at 5B, it doesn't get to this part until it has gone through the middle, the body of the loop. The first thing we do is to try to find a prime factor f of 1. The algorithm that we use starts with 2. Okay? What is 1 mod 2?
1/2.
No. What is the remainder of 1 divided by 2? I got 1 candy, and I have to divide it equally to 2 kids. What is the remaining portion that I have once I evenly distribute the candy to both kids? I got 1 candy left because none of the kids is going to get anything, right? So 1 mod 2 is 1. What about 1 mod 3? 1. 1 mod 4? 1. So what happens to that loop inside find prime factor of n? It becomes an infinite loop. Okay? It becomes an infinite loop until f goes all the way around the big number wheel back to 1 itself. Then 1 mod 1 is 0, and then we can get out. But that's still incorrect. Okay? Even though it will give you the right result, it is still incorrect. So 5B cannot handle that case. What about 5A? Can 5A handle the special case when n equals 1 to begin with? Yes. Will we get into trouble? Nope. Because what happens when n equals 1 to begin with 5A? It just skips the whole loop. Okay? It doesn't print anything, but at the same time, it just skips around the whole thing because it only gets into the loop when n does not equal to 1. So if you start with the condition that n does equal to 1, it simply does not do anything. Yep.
What if 0 goes in there? What's 0 mod or whatever?
Well, if you put 0 in, then both will give you the incorrect result because 0 is not a factor of anything. But it will still be able to do it because 0 mod 2 is what?
0.
Exactly. So the loop will exit and it will misidentify 2 as a prime factor of 0. So it will still get out of the loop, but it will give you the wrong answer.
So should you put while n is not equal to 1 and n is
In
not
this
equal
case,
to 0?
for this algorithm, there's one easy fix to it. You can just say that don't feed anything less than 2 as an integer to this algorithm.
Okay.
That will stop it. You can make rules to your algorithm. You can say this only works when n is an integer and it is greater than or equal to 2. And that's all you have to do. And that's your precondition. See, your precondition is helpful because now you can say, to make this algorithm work correctly, you have to give it variables that will fit these conditions. So the precondition is useful because now you can make constraints and just say that you cannot give it any other number. Yep.
That's the true and false precondition thing.
Exactly.
Talk about it would be a dead branch with 0
Yep.
and 1.
In other words, when the precondition cannot be guaranteed, neither can the post condition. Okay, that's it for today. So don't be late on Thursday because we'll have a test. Someone's going to forget.
Yeah. I thought it was today.
Well,